Greetings. So, as I mentioned earlier, I had mentioned earlier that Einstein had these three portraits in his study: Newton, Faraday and Maxwell. And the work of everybody from Coulomb, Ampere, Oersted, Biot-Savart, Faraday, Lenz, Henry, everything comes together in Maxwell's work, and then Maxwell's work becomes the foundation for Einstein's theory of relativity, the special theory of relativity. So, we concluded that if you know the divergence and the curl of a vector and the normal components at the boundary of the region in which these vector fields are defined, then the vector field itself is uniquely defined, which is what makes Maxwell's equation so important. There is another theorem of importance over here, that if you have a vector field whose divergence and curl are both known to vanish asymptotically, they go to 0 as r goes to infinity. That is what vanishing asymptotically means, all right. Then such a vector field can always be written as a sum of one irrotational vector and another which is solenoidal. An irrotational vector is one whose curl vanishes, and a solenoidal vector is one whose divergence vanishes. Now, this is very important because this will tell us what kind of potentials these fields are derivable from. Okay? Now, that is going to be another important aspect of electromagnetic theory, which is the use of potentials. So, we are going to be led to that through this theorem, which is called as the Helmholtz theorem, and we know that since the curl of a gradient and the divergence of a curl always are 0, essentially what we are aiming at is to show that if you have a vector field whose divergence is known and whose curl is also known, divergence is given by the scalar field S, the curl is given by the vector field C, both of these are known, then you can write the vector field K as the sum of a rotational vector and a solenoidal vector, and an irrotational vector can always be written as a gradient of a scalar, and a solenoidal vector can always if you have a solenoidal vector, then you can write it as the curl of G, where G I will be defining shortly. Okay? So, you can write it as a solenoidal vector because the divergence of the curl of a vector is always 0. So, it will have to be the curl of some vector field G, because the curl of a vector field is essentially solenoidal, its divergence always goes to 0. So, this is the Helmholtz theorem. So, let us use what we know. What we know is that the divergence of the vector field is known, it is given by the scalar field S. The curl of the vector field is also known, it is given by the vector field C. And using this, we can now define a function psi, a scalar function psi, and a vector function G, which I mentioned in the previous, when we were discussing the previous slide. So, the left hand side can be constructed from the right hand side in any mathematical equation. On the right hand side, you have got an integral involving integrands which are defined in terms of known functions S and C. So, there is no difficulty constructing the integrations right hand sides, and therefore, you can construct psi and G. Okay? Now, I am going to use the following notation, which we have used earlier also, that whenever we talk about the field point and a source point, I have used r prime for the source point and r for the field point. The difference vector r minus r prime I have used represented by uppercase R with a prime because you will have to integrate over the source points, right. And you talk about a causal relationship, that the cause determines the effect. So, you have got a source which determines an effect at the field point, right. Now, this is what we know so far. We know the curl of the vector field, we know the divergence of the vector field, and using this curl and the divergence, we have now constructed two fields, one a scalar field psi and another a vector field g. And if we can now show that this vector field k can be written as the sum of minus gradient psi and the curl of g, then we are done, right. That is what the theorem requires us to prove, that we have to show that if the divergence, the negative divergence of psi or the del square psi is equal to S of r, and if the curl of g is equal to CR, then we would have proved this theorem, which is known as the Helmholtz theorem. So, let us proceed to prove this. So, we take the divergence of del psi. Psi we have constructed from S, which is known, right. The divergence is with respect to the field points. The integration is with respect to the source points. These two are independent operations. So, the differential operator del can be moved inside the integration, and it can now operate on the integrands, of which the part of the integrand, which is the numerator, which is SR prime, will remain unaffected because it depends only on the source. So, you really need to consider del dot del operating only on 1 over distance, okay, because the distance is the distance between the source point and the field point, and the source point is integrated out, but the field point is the one with respect to which you have to take the differentials. Okay. Now, this we know because this is given by the Dirac delta. We have used this earlier. Okay. So, del dot del operating on 1 over distance is 4 pi times the Dirac delta. This is known, and now we can carry out a Dirac delta integration, and we already find that minus of del dot del psi is equal to S. So, one part we have already proved very easily in one step integration using the Dirac delta. Now, we still have to show that the curl of G is exactly equal to C, which is what we started out with. Okay. This is what we now have to show, that remains to be shown. So, let us determine what is the curl of G, and we write it as a difference of two terms, T1 and T2, and we will handle them separately. Okay. So, we have used a vector identity over here, which is valid for any vector function, and we first determine the term T1, which is the gradient of the divergence of G. So, we determine the divergence of G first, and the divergence of G involves the divergence of the integral, which is integration over the source, which is the primed variables. The differential in the divergence operator are derivative operators with respect to the field point out there. So, these two are independent. So, you move the divergence in, and now you have the divergence of C r prime over r minus r prime. So, you separate out the terms, okay, right. Now you have to be careful because this involves derivative with respect to r and the integration is with respect to r prime, right. So, is this, can I show this to be 0? Is the divergence of a curl equal to 0? No. This is differentiation with respect to unprimed variable, which is the field point, and this is the curl with respect to the primed variable, which are the source points. So, I cannot throw this term. But what I can do is I can write this as C dot del prime dot gradient with respect to the source points, because here you have got a minus sign. You have got the modulus of r minus r prime, and r prime are completely symmetrically situated except with respect to the sign. So, when you take the derivative with respect to the unprimed variable, it is equal to the derivative with respect to the primed, but with a minus sign. So, you use that, and having used that, so let us put it over here. So, now we have put this minus sign over here, okay, and now put it in this integration. Now that you have it in the integration, you now have the derivative with respect to the primed variable, and this c is also with respect to the primed variable. So, now you can set it equal to 0. Okay? Now there is no problem, and you can write, this is the volume integral of the divergence. Actually, there is a volume element over here d3v prime. So, this is common to both of these terms. So, this is the volume integral of the divergence, which you can now write as the surface integral over the surface which surrounds this region using the Gauss's divergence theorem. So, using that, we now have a simple expression. Now, where is this surface? You can take this surface in the asymptotic region to surround all the volume that may be there of your interest. And the surface out there is going to increase as r square, right, distance square. You know that the solid angle goes as r square d omega. So, the surface increases as r square, and now you have got 1 over distance and c. So, as long as you have c, if it diminishes at least as fast as 1 over distance square. Okay, if it diminishes faster, it is even better, but it does not matter. Even if it diminishes as fast as, at least as fast as 1 over distance square, then 1 over distance square of the vector field c will cancel the distance square in the numerator, and you are still left with the 1 over distance in the denominator. Okay? And the surface integral will eventually vanish. So, the divergence of g goes to 0. If the divergence of g goes to 0, then now you have the two terms T1 and T2. You know, T2 becomes the del dot del operator operating on this integral, and the differentiation in del dot del in the Laplacian is with respect to the field points, the integration is with respect to the source points. So, you can move in this del dot del operator, get a Dirac delta and wrap it up, because the Dirac delta is this lovely shifting operator which gives you the value of the integrand at a particular point. So, that proves the Helmholtz theorem, that you can write this vector field in terms of a solenoidal and an irrotational vector. So, this is an amazing theorem which really helps us develop the potential theory. So, I would like to suggest for further reading a paper by Zhao, which you might find useful, but I will not discuss this paper in our course. So, we have proved the Helmholtz theorem that a vector field whose divergence and curl are known and they both asymptotically vanish, then it can always be written as the sum of an irrotational vector and a solenoidal vector. And a solenoidal vector you can always write as the curl of an arbitrary vector field, and an irrotational vector you can always write as the gradient of an arbitrary scalar field. So, it does not matter what size, it does not matter what G is, but these relations will always hold. All right. So, this is the Helmholtz theorem. We had already proven the uniqueness theorem in the previous class, all right, that if you know the divergence at the curl of a vector and if you also know the normal components, you can get that vector field uniquely. So, let us compile all our understanding so far. So, you have got the Maxwell's equations, you have got the Lorentz force law, and because the divergence of B goes to 0, you can write B as the curl of a vector because the divergence of curl is always 0. Now, this is leading us to the potential theory. What it tells us is that the magnetic induction field B, or the flux field B, is derivable from a vector potential A. That is what you call as a potential. Potential is the field, it is the vector field from which the magnetic induction field B is derivable. All right. So, this is called as the vector potential, and because it gives you the magnetic field, it is called as a magnetic vector potential. So, now we are introducing the potentials. Okay. And the potentials in fact will become quite important in our discussion. So, this is coming from the fact that we know that the divergence of a curl is 0, right. And if B is equal to del cross E, del cross A, then since we know that the curl of E is minus del B by del T, which is the consolidation of the Faraday-Lenz law in Maxwell's theory, right. We replace this B by the curl of A, and now we get the curl of del A over del T with a minus sign, because differentiation with respect to space variables and differentiation with respect to time variables are independent. Okay. So, if you bring the left hand side and right hand side together, you find that the curl of this quantity is equal to 0, which means that E by itself is not irrotational, but when you add the time derivative of the vector potential, then it is. And if it is irrotational, you can certainly write it as the gradient of a potential, okay, because any vector field which is irrotational can be written as the gradient of a potential, because the curl of the gradient of a potential is always 0. All right. So, elementary results of vector calculus are coming in handy, and this is really what seamlessly integrates mathematics with physics. It is absolutely seamless. You do not look at one as mathematics and the other as physics. The potentials in fact are very physical, they are coming out of these equations, and they are very physical. So, what is the electric intensity field itself? It is minus del phi plus del A by del T. So, certainly it is equal to minus del phi, which by itself is completely irrotational in steady state phenomena. But when the phenomena are not steady state, then you must add the del A by del T to make it irrotational. Okay? So, you have got a solenoidal field, and now starting with that we are led to the electromagnetic potentials. There are 4 of them: phi, which is the scalar potential, and then the 3 components of the vector potential, so total 4. Okay. And what we have as irrotational is the sum of E and del A by del T. The potentials become extremely important in quantum mechanics. Means if you are not getting into the domain of quantum mechanics, one might suspect that, okay, what is the use of these potentials, because I can add anything to the potential and still get the same field, because the field is only the gradient of the potential. So the gradient of a constant will go to 0, so it does not matter. So what is important about potentials? Why should I even study them? So it turns out that in quantum mechanics the potentials in fact become even more important. And there is a famous experiment by Aharonov-Bohm, what is called as the Aharonov-Bohm effect. I will discuss it when we discuss quantum mechanics, and they will make the potentials even more important. So we need to prepare ourselves for that. And of course, they also have very important applications in classical electrodynamics, in classical phenomena also, because they make the analysis of many problems in electrodynamics very easy to analyze. So you have got the electric fields and the magnetic fields given by the gradients or involving the time derivatives of these potentials psi and A, phi and A. Okay. And notice that since the curl of a gradient is always 0, the curl of the potential can be either A or A minus del psi. You will get the same field. Likewise, the potential can be phi or minus del psi by del t, and you will get the same electric intensity. So these are known as gauge transformations. So what are gauge transformations? You know what is a gauge? Gauge means to measure. And in the railways, for example, in India, you have got the narrow gauge, you have got the meter gauge, you have got the standard gauge, then you have got the broad gauge, right? And these are different measures of the distance between the two rails. And no matter what gauge you are using, you can go from one point to the other. So it's the same kind of thing that we were talking about, that no matter what potential you use, you will achieve getting the same fields, right? So in that sense it is similar, which is why these are called as gauge transformations. This is also used when you are looking at gauge of thickness of various metal sheets. You can measure this gauge in terms of some millimeters or inches, and there are sheets of different gauges, 25 gauge, 22 gauge. So that is a common vocabulary which people use, all right, when you are using machines. And likewise, you have these gauge transformations. You can transform from A to A minus del psi and from phi to phi minus del psi by del t, and you will get the same fields, all right. So these are known as gauge transformations. And now the question is, how do we choose the gauge? Because now you have got huge possibility, all right. Different gauges can be used. What criterion do you want to use? You will like to use such a gauge as would give you fields which are consistent with Maxwell's equations, okay, because we have put in a huge amount of effort, consolidated all the semi-empirical laws of Coulomb, Ampere, Faraday, Lenz, everything together in the one umbrella of Maxwell's equations. And we know that they are the ones which we should be using to study electromagnetic phenomena. Then we should use a gauge such that the Maxwell's equations are satisfied. So that is now the criterion that gives us like the guiding force, the guiding principle to choose the gauge, okay. Now that is not very easy because Maxwell's field equations are coupled partial differential equations. Okay, E and B come together. The consequence will be that A and phi will come together and it will become messy, complicated, difficult to solve the equations for A and for phi separately because of this coupling. So, we have to devise a mechanism to deal with that. So, that is the challenge we have to work with. So, let us see how they get coupled. So, you have this Coulomb-Gauss-Maxwell equation. We have agreed that E can be written in terms of the potentials phi and A. Okay. So, if you now take the divergence of E, then you have this relation in which you have got the differential of phi, but you also have the derivatives of A, and the equation for phi and A are coupled. So, this is the challenge, all right. Got it? Now, what you also have is that the curl of B is curl of the curl of A, if B is derivable from the vector potential A. Then you have this vector identity, right, and the curl of B from Maxwell's equation is given to be this, but del E by del T is now, since E is given by minus of del phi plus del A by del T. So, that is the term that will come here, and these two equations must agree. So, this is coming from the vector identity, this is coming from Maxwell's equations, and they have to be consistent with each other. The left hand side of both is curl of B, the right hand sides are different, one is in terms of the potentials and the other is in terms of vector operations. So, the right hand sides of the two equations must be necessarily equal. So, let us do that and demand that the right hand side of the two equations must be equal. So, equate the right hand sides of the two equations. Okay. That is what we have done now. We have the right hand sides equated, and notice again that we have got A, derivatives of A and also derivative of phi. You also have the time derivative of A, which is here in the last term, and you also have the time derivative of phi over here. So, the time derivatives are there, the space derivatives are there, and they are all coupled. It is a mess. How do you get them if you do not know either of them, right? So, this equation you just simply rewrite. I have only put mu 0 j term on one side with a minus sign and all the other terms on the left side. So, this is no different from the previous one except that rearrangement of the terms. And now, when I look at this, I find that if this second term goes to 0, then I am left with an equation only for this side, and this one does not have phi. So, I have decoupled A and phi. So, by choosing this second term to be 0, how do I do that? I put del dot A equal to mu 0 equal to minus of mu 0 epsilon 0 del phi by del T. If I choose the divergence of A, can I do that? Yes. What helps me do that are the two theorems that we just discussed. Okay? The curl alone does not select the vector field. The curl and the divergence together with the normal components selects the vector field. Now I have that freedom. I have chosen the curl already, I cannot tamper with it. What choice have I made? I have made the curl to be such that the curl of A is equal to the magnetic induction field B. I cannot tamper with it. That choice I have already made. But the divergence of A, I am still free to choose. and I exercise this freedom to choose the divergence of A to be equal to minus of the second term, so that it vanishes, because that helps me decouple the differential equation for A from the differential equation of phi. Okay? The other choice I can make is I can put the divergence of A equal to 0, and if I pick the divergence of A to be equal to 0, then from this other coupled equation which I had for phi and A, which I showed on the previous slide, then in this the divergence of A goes to 0 and I get del dot day del phi equal to minus rho over epsilon 0, which is what I have written over here, and this is nothing but the Coulomb-Gauss Poisson equation. Okay? So I know how to solve this, and by solving this I can get phi, and once I know phi, then I am not worried about the coupling, because one of those is already known. Okay? So I can use either of these two choices. So one is called as the Lorentz gauge, which is the choice divergence of A equal to minus mu 0 epsilon 0 del phi by del t. The other is called as the Coulomb gauge, which is divergence of A goes to 0, and I can achieve decoupling through either of these two methods. Okay? Now when you look at this equation, you tend to get a feeling that okay, you are ignoring the consequence of the special theory of relativity, that you've got the cause at the source, whereas the field is experienced at the field point, right? And then how is this that this is happening at the same instant of time? So you don't have to worry about it, because the electric field itself has got a time dependence, and then when you work it out, you can resolve this issue. So let us discuss the Lorentz gauge, and in the Lorentz gauge del dot A is equal to minus mu 0 epsilon 0 del phi by del t, and in the Lorentz gauge this second term vanishes. So you have got this left hand side, which is this, equal to the right hand side, which is this. Okay? So you have got similar looking relations, okay, and you can write the two equations in terms of what is called as the box operator. This is just a compact notation, there is nothing more about it. It is what stands for the Laplacian and the second derivative with respect to time, and you can write the same equations, and in the steady state phenomena the time derivatives vanish, and in both cases you have essentially Poisson equations. Okay? In one case you have got the scalar Poisson equation, in the other case you have got the vector Poisson equation, but you can break it into like 3 scalar equations and solve for each component if you like, and the solutions are given by this. Now you can obtain this as a solution to the differential equation. Notice that the solution is in terms of charge over distance, which we know from the potential theory in Coulomb's law. Okay? It is not a surprise that that was accurate, because the theory is completely consistent, but it is not obtained as a statement of the superposition of the Coulomb potential. It is written here not as a statement of superposition of the Coulomb potential. It manifests like that, but it is obtained as a solution to the differential equation, which is the Poisson equation. Okay? How do we know that the solution is correct? Carry out the integration. Okay, get the divergence of the gradient of 1 over distance, use the Dirac delta. Okay, this is such a powerful, beautiful function, right? And using the Dirac delta integration, you can see that the solution to the Poisson equations are essentially correct. So, that is a straightforward thing. Dirac of course was a brilliant physicist. It seems that he was not very fond of poetry. He says that the aim of science is to make difficult things understandable in a simple way, whereas the aim of poetry is to state simple things in an incomprehensible manner. Einstein met Tagore, but I don't think Dirac did. It would have been interesting to know what they conversed, what they would have conversed with each other. So, anyhow, these are the solutions of the Poinsot equation, and we know that they are correct. They are not written here as superpositions of the Coulomb potential, which we knew from empirical laws, but from solutions of the Poinsot equation that we have arrived at from the potential theory, right? And in both the expressions, we have got the 1 over distance. We know how to deal with that, so I will quickly recapitulate this. The distance square in this triangle is given by the cosine law. We have discussed this earlier also, so I will go through this a little hurriedly, but it is important to recapitulate some of these terms, which I will do. Okay? And you can write this as a power series expansion of 1 plus xi to the power minus half, where xi is written in terms of this ratio r prime over r and the angle between the field point orientation and the source point orientation. Okay? So, between these two angles you have got the cosine of the theta, and you can write the 1 over distance in terms of this Legendre polynomials that we have discussed earlier, right? We discussed this in one of our earlier discussions. So, I will not spend any big time on this, but it is essentially the same power series expansion which I have plugged in over here for 1 over distance, which appears in the solution to the Poinsot equation. So, look at the vector potential. Now, the first term is r prime to the power 0, which is 1, p0 cos theta is 1, and you are simply carrying out a closed loop sum of dl prime. So, you are taking segments and add them to each other till you go to 0. So, displacement vectors which are added to each other, the tail of the next is sticking to the tip of the previous till it comes back and closes the loop. So, the net displacement will go to 0, which is fine, which is what we should have hoped for, because we have in our theory formalism the divergence of B to be 0. So, there are no source monopoles for that. Then you have got a monopole term, a dipole term, and so on. So, you can write these terms for different powers of L as a multipole expansion, all right. So, the term for L equal to 0 vanishes. So, there is no monopole term, and then you have got a dipole term. You can write it using some vector calculus, which is not very difficult. You will find detailed analysis in Griffith's book and also in this Foundations of Classical Mechanics, which is my book, which is about to be released, right. So, all those details are worked out over there, but you can also work it out as a homework exercise or use Griffiths if you like, all right. So, you have got the dipole term, and notice that it has got a structure which is current times a surface area, current times a surface area, and you can represent this as a magnetic moment. This is what you will call as a magnetic dipole moment, okay. And this is current times area. So, if you take a small area and have a current in this conductor which surrounds this area, so there is nothing in that area, the only thing that you have got is the current which is going around this area, then it has got a magnetic moment which is current times this area, and this area is the cross product of two vectors, which is an axial vector. So, the magnetic moment is also an axial vector, okay. So, the magnetic vector potential, so all of these you have to keep track of how they transform under rotations and how they transform under parity. So, you have got this, the dipole moment potential, which is m cross r. Now, let us have a quick look at what we have got so far. We have got the Maxwell's equations, and in these the sources of the electric fields is either an electric charge. The electric charge is of course free to move. It is not necessarily, frozen at one point in space. But you can also have an electric field from a time dependent magnetic field. Okay, that is what the electromotive force in the Faraday lens law was about. Likewise, the magnetic field you can get from an electric current, which is what was known to Oersted, Biot, Savart and Ampere. But then later, as Maxwell discovered, we could get it also from the time variation of the electric field. So, the sources of the electromagnetic fields are now becoming more diverse, not just a charge in the sense of the Coulomb's law, but also a time varying magnetic field where there is no charge, no physical charge. A physical charge like an electron which has got a mass, which has got a charge and a mass, right? In a changing magnetic field, right, you do not have any particle of that kind, but you just have the magnetic field which is time dependent, and that can also create the electric field. Is this electric field any different from the electric field generated by a charge like a charged particle? No, it is exactly the same field. There is absolutely no difference. Likewise, the source of a magnetic field is an electric current, as was known to Ampere, Biot, Savart, Oersted, right? But also a time varying electric field, del E by del T, that also gives rise to a magnetic field which is no different from the magnetic field you would get from a current. The same effect, but the reasons are completely different. Okay? No matter what the source is, the fields are of the same, they have got the same physical properties. Okay? No matter what the source is. But then there are other sources which are possible, which we did not mention as far as the previous discussion. Some sources are still left out. They also generate exactly the same kind of effect. What kind of source? You may have a dielectric material, and the dielectric material, you may have the centers of the positive and negative charge. The material on the whole may be neutral, but the positive and the negative charge are displaced. And if they are displaced, you have these tiny dipoles throughout the region of the dielectric. Okay? You may also have a magnet, which also generates a magnetic moment. So, there are these additional materials which can also lead to the same kind of effect, and we will have to factor them into our potential theory. Okay? Now, in the magnet, you do not have these current loops at different places in the magnet. The source of this magnetism is described by accurate laws of physics which were not known at the time. These laws of physics, which are more accurate than the laws as were known earlier, these laws of physics require quantum theory. These laws were not known earlier. And as a result of the this new understanding that we have, we are now able to understand this additional source of magnetism which some materials have. They do not have charges going in orbits which are generating this magnetic moment. Okay, a charge going in an orbit like the Bohr model of the atom, which you might have studied in your high school or even in college, those models are not correct. Because what is an orbit? An orbit is like a planet's motion around the sun. That's an orbit. And you can define an orbit only if you know its position and momentum together. And position and momentum are not simultaneously measurable. Measurement of one destroys information about the other, as a result of which you cannot even talk about orbits. So, there are no real orbits. But there is magnetic moment, and you need a new theory. This new theory is not from classical mechanics, you need quantum theory for this. Okay? The effect is the same, that as a result of the new theory, there is additional source of intrinsic angular momentum which particles have, and as a result of this intrinsic angular momentum, there is a magnetic moment which is proportional to that. And because there is this magnetic moment, it now generates a potential at a field point. And now the previous theory that you developed about the potential theory can be used, but with an additional source. So, this additional source is the quantum intrinsic magnetism. Okay? So, this is where I will conclude today's class, and we will pick up the discussion from here. If there are any questions, we can certainly discuss them now.
Sir, we have seen in the gauge theory that field is unique but potential is not. And we are saying that we can have different sources for same field. Sir, is like both are complementary of each other, something like that?
They are not complementary, they go together. They go together because, you know, for both potentials and fields, the principle of superposition operates. So, no matter what the source is, the source of a field, the source of a magnetic field can be a current flowing in a wire, or it can also be this intrinsic magnetic moment of some particles which are sitting in matter which is in the vicinity. The nature of the field generated by one is no different from the nature of the field generated by the other. And the two fields will superpose at the field point. The net field will be the sum of the two. The principle of superposition holds. It can also come from the changing electric field. So, all of them will add up at the field point.